think it's quite a big area. I mean, when I first was thinking about this talk, I was going to call it Everything We Don't Know About Astrophysics. And I quite quickly found out that's a very, very, very large area, very big topic. So I had to bring it down a little bit, just to the most interesting unsolved mysteries in astrophysics. But I'd say throughout kind of human history, for the last several 100,000 years, people have looked up towards the sky and wondered about what we saw up there. And it's only really in the last sort of 300 or 400 years we started to get a really good idea of what it is we're actually looking at. Stars, the galaxy, nebulae, other objects. And really only in the last 100 years we started to get a good idea of the really size and scale of what we were looking at. It was only 100 years ago that we proved other galaxies even existed in 1924. And it's really only in the last 3 or 4 decades we started to get a good idea of the bigger forces at work and the actual start of the universe and maybe how it will end as well. But it's easy to forget in all of that and all our modern science and technology and telescopes and space missions that there's still loads of stuff we don't actually know. Probably way more stuff we don't know than what we do know. So I think it's worth to go through a few of the things that we don't know and see where the kind of modern frontiers of science actually are. So I picked a few things. Hopefully I have time to get to all of them. As I said, there's a lot we could talk about in this. So let's start actually with, let me turn this around, some of our neighbors actually, and even the closest neighbor we have. This is an image of Venus. And Venus is the planet that comes closest to us. But actually there's a great deal of things that we don't know about Venus at all. So this image is taken in radar. So this is in the early 1990s. So this is an image of the surface of Venus, underneath the hugely thick layers of clouds. So when you look at Venus in the telescope, you tend to see a sort of featureless disk, or maybe a crescent shape, because it's got these thick clouds on the outside. And in the 1990s, we managed to look through these clouds using radar images. We see quite a few interesting things. So first of all, we have all these cracks across the surface, right? These kind of fairly obvious ones here. These are a result of volcanic activity, mostly. And the other thing we see, or rather we don't see on here, is craters. So there's remarkably few craters on Venus's surface. If you compare it to something like our moon, right, which is covered in craters, right? Because our moon is not changed, the surface has not changed very much apart from craters hitting it in the past sort of 4 billion years or so. But we don't find many craters on Venus. Does this mean that asteroids have not hit Venus? Well, no, of course not. We've had a lot of asteroids that hit Venus. And when we try and age the surface, what we find is that the whole surface seems to be a similar age, and that age is about 500 million years old. And that seems to suggest that the whole surface was altered about 500 million years ago. But we don't know how. We don't know what exactly it is. We just know that something, some kind of global event, possibly a global volcanic event, has changed the surface of Venus, and then since then it's stayed fairly static apart from further smaller volcanoes and these cracks that we see across the surface. So it's still a big mystery, really a big matter of conjecture about what exactly this resurfacing event was. How quickly did it happen? Did it happen in the course of 1 million years? Did it happen in the course of 10 million years or more? We don't really know. We don't really understand the history of Venus very well at the surface at all. We have landed 4 times, I think, on the surface of Venus, but not for a few decades now. Actually, it's incredibly hard to get any data on the actual surface composition of Venus because it's so hot on there, about 400 degrees Celsius on the surface of Venus, and the atmosphere is incredibly thick down there. So on that surface, the atmospheric pressure is kind of similar to about 1 kilometer below Earth's oceans, right? Incredibly thick and huge quantities of sulfur dioxide, acid, in the atmosphere. That means the probes that we have landed on Venus lasted about 30 or 40 minutes before breaking down, right? So it's incredibly hard to get surface samples of what's actually going on in Venus to kind of give us an idea. And then if we go further up as well, we can look at this is usually what we see when we look at Venus, right? We've got the cloud layers, this is visible light, this is what we see in visible light. This one is an infrared light, so we can look through the cloud layers a little bit more. And there's a few interesting things we find here as well. First of all, Venus itself, the planet, rotates about 2 times for every 3 Earth years. Is that the right number? 3 times in every 2 Earth years, sorry. So it rotates very, very slowly. But actually, these clouds are whipping around much, much faster. These cloud features make it all the way around the planet in about 4 days. So the clouds are going way, 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 way faster than the surface is going. We don't really have a good explanation yet as to what the cause of this actually is. Why they're going so much faster, what is causing this huge super rotation of the clouds. And higher up in the cloud layers, we have recently, in the last few years, had some very intriguing detections of a chemical called phosphine. So phosphine here on Earth is a chemical that is only really created by bacteria. Not created it's created in small quantities in volcanoes, but very, very, very small quantities. Not in the kind of quantities that we've detected high up in the cloud layers in Venus. Now, since this detection, there's been a few, as always in science, there's been a few other studies that suggest maybe it's overblown and we're not really sure. So there's been a bit back and forth on this one. So we are planning missions at the moment to actually go into these clouds and see if we can directly detect these chemicals. Because we're just looking at the light signature from the planet is how we've made the detection, but we haven't actually gone and physically found them. So that is kind of coming up. So again, some people think this could mean that there is bacterial life hanging around in the upper layers of the atmosphere. It's a lot less hot, a lot less dense, and perhaps easier for life to exist. So maybe we will find out in the next few years if there's life in the clouds of Venus. We shall find out. Sticking in the solar system, the other kind of main candidate for life at the moment is in some of our icy moons. So we have quite a few icy moons that seem to exist out in the solar system. It seems that water is actually incredibly common, at least in our solar system. We can probably infer throughout the galaxy as well. On the right here, we have an image of Europa. So this is one of the moons of Jupiter. On the left, we have one of the moons of Saturn that we call Enceladus. So there's a very interesting story with these kind of moons. So when we first visited Europa, or Jupiter, in the early 1980s, we expected this moon to look, again, much like our moon, covered in craters. A little bit similar to Venus. Again, we can see very, very few craters on here. We can also obviously see these big cracks, right? So this is a huge surprise to these astronomers when we got these images back. And actually this whole thing was live broadcasted in the United States, so you could watch all the astronomers being completely confused by what they're seeing, which is great watching, it's very funny. So we had these big cracks here, pretty much worked out pretty quickly. This surface must be being regenerated, and it must be ice, right? So we see an ice moon. Well, that was a surprise in itself. Well, we went back in the 1990s, and we find when we did measurements of the magnetic field of this moon, what we find is that there seems to be huge quantities of liquid water underneath the surface. Again, a huge surprise, because we thought this was basically far too far away from the sun to be warm enough for liquid water. We believe the mechanism that is causing this is Jupiter's immense gravity. As this moon goes around Jupiter, it's being squashed and pulled and distended, like a squash ball that you rub beneath your foot. And so it's heating up on the inside. And because it's heating up on the inside enough to allow this water to exist. And the measurements suggest there's more water, more liquid water under the ice here than there is on the whole of our planet Earth. So huge quantities of water, and very salty as well. Jupiter's not the only one. So this moon of Saturn, we call Enceladus, also seems to exhibit the same thing. What we found when we visited Saturn in more detail in the 2000s with the Cassini space probe was that there was plumes, what we call cryovolcanic plumes, coming out of the surface. So we could see it when we photographed it against the sun in the background. We could see this material being ejected out. We actually managed to fly a probe through one of these plumes as well. And what we found was something we call organic molecules. Organic molecules does not mean life. What it means is all the building blocks that go on to create amino acids, which is where we get DNA and life. So all the ingredients we need for life exist on these moons. So we have water, we have heat, we have organic molecules. We maybe have kind of hydrothermal vents underneath the ice here, because we have a rocky core on this moon, potentially hydrothermic vents there. And everywhere on the Earth where we find water, we find life. And we see all the ingredients for life on these moons. So again, these are of extreme interest to astronomers. We have and physicists. We have several ongoing missions at the moment to go and look at these. So, oh yeah, before I go into that, this is an image, or rather a video, of a nearby star about 130 light years away, where we can see four massive planets going around. So in the last sort of 30 years, we've detected a large number of what we call exoplanets, so planets around other solar systems. This is just a rather nice video. This is actually these are the first exoplanets we managed to image directly. We can see them going around. They're all in quite big orbits. They're all bigger than Jupiter. They're very, very large orbits. This one out here is going to take, I think, was it more than 500 years to go around one orbit. So it's quite far away from the planet. But to give us an idea of the number of other planets that are out there, right? We go up into the night sky and we see many, many, many stars. If we imagine that the stars have so many planets like this, how many different configurations of planets and waters and moons and heat from stars and everything else are out there, suggests to us that there's every chance maybe that life could exist around other stars. And intriguingly, with some of these exoplanets, with this kind of configuration, they're all going around like that, right, from our point of view. Sometimes the orbits of the planets are flat to us compared to the star, so we can actually see the planets going in front of the star. And very occasionally what we can do is when it transits in front, through the atmosphere of that planet, using the star's light in the background, to get an idea of the chemical composition of the atmosphere of that planet. So, very recent one that came through about 120 light years away from us, we find another chemical that we call dimethyl sulfide, which again is a chemical on Earth that we associate with life. We have not found any way of producing this chemical naturally, not from life. So it's a very, very intriguing possibility that this chemical is produced by life. Now, it's worth saying that other studies have disputed this. Again, this happens with science all the time. This is how we work science. So other studies have disputed this. So really, in the next months or years, we might get a better idea of whether this chemical is really there or if it's a bit of a mistake in the way that we're analyzing it. Once the James Webb Space Telescope has had a good chance to look at this in more detail. So again, more intriguing hints that maybe we're not special, that maybe there's not just the ingredients for life everywhere, but maybe actually life. We shall see, I think, in coming decades. In terms of our solar system, what is actually coming up here? So both NASA and the European Space Agency have missions on the way to Jupiter to look at these icy moons in more detail. So NASA is sending the Europa Clipper to Europa to look specifically at what we can find there, which is going to do 50 flybys around Europa, as low as 25 kilometers above the surface. The European Space Agency is also going to Europa, but also to other icy moons around Jupiter. So we call it JUICE, the Jupiter Icy Moons Explorer. Mainly to look at one of the ones we call Ganymede, which also is extremely interesting moon, but also Europa and Callisto as well, which is the other icy moon. And a bit closer to home, this third one we have here is a mission that is a collaboration between the Massachusetts Institute of Technology, MIT, and an organization in New Zealand called Rocket Lab. who are sending what they call the Venus Life Finder mission, which is maybe a bit grand as a name because it's not actually got the capacity to find out if there is life there, but it is about what it's going to do is dive into the Venus's atmosphere and try and find evidence of other organic molecules in there, and that should be happening within the next kind of few years. So we have a number of missions coming up to try and kind of find out about these mysteries a little bit deeper. Let's see how we're doing. Yeah, we're good. So that's in our solar system. We can go a little bit further and talk about the universe at large. So when we go and add up all the stuff that we can see in the universe, it doesn't really seem to be enough of it. The models don't work in various different ways. And probably the one that we've heard most about, has generated a lot of interest in the last 50 years or so, is dark matter. So it was actually the first person to think about this was nearly 100 years ago already. A guy in 1933 looked at a cluster of galaxies. So galaxies in a giant cluster, we get several galaxies that are close together. Looked at all the matter in them and worked out that the galaxies should all be flying apart from each other, but they weren't. So there was some extra matter that we couldn't see. Nobody really paid that much attention to it for a little while until the 1970s, when we got this plot made. So what we are looking at here is the distance from a galactic core, so the core of our galaxy here, the distance away from the core, and we measure the speed that the stuff is rotating around, so both the stars and the hot gas inside there. What we would expect to find from the models, based on how much mass we think is in there, is that the speed as we get further away from the core, initially get more, and then the speed should decrease as you get further away. The same way that the further out planets in our solar system orbit slower than the close by planets. What we actually find is this, is that it doesn't seem to decrease at all. In fact, maybe even slightly increase as we get further away from the center of the galaxy. So the stuff on the outside of the galaxy is rotating around at the same speed or faster than the stuff in the middle. This was the first really proper evidence of there being much more matter around galaxies, and it seemed to exist around in a sort of halo around galaxies than we could actually see. Now, recently, there's been some very, very interesting observations done. So what we're looking at here is something called the bullet cluster of galaxies. This is one of the most high energy events that we have seen in the universe. What we're looking at is two clusters of galaxies that have collided. So we can see one on this side. So this smaller cluster has collided straight through the center of this bigger one. So we have the stars themselves that we're used to seeing, these kind of galaxies. These have been largely unaffected by this because there's still huge distances between each of these galaxies. So they've kind of just sailed straight past each other without much really going on. These red areas are hot gas. So in terms of the matter we know about, normal matter, stars, gases, about 76% of it exists outside galaxies. So actually much more matter exists between galaxies than in galaxies. We can see this when we look in X-rays. So these red areas are X-ray images of hot gas that exists between galaxies. And we can see this is the cluster, this is the hot gas, and again this is the cluster and the hot gas. It is lagging behind these two clusters. So although the galaxies themselves didn't really interact, all the stuff in between galaxies did. So this hot gas passed through each other and then interacted electromagnetically and was slowed down. So the hot gas was slowed down by this merger. And then these blue areas, what this is when we look at something we call gravitational lensing. So things that have a very strong gravity bend light around them. This is one of Einstein's big ideas. So what we can do is look at the light from distant galaxies, especially galaxy clusters, and see the light that's bent around them to get an idea of how much mass is there. So we can kind of see like this funny little line here and some other smeared out bits there and there. This is light that's bent around this cluster of galaxies and kind of has a lens effect. So we can do this and we can work out how much mass must be here. Where we find most of the mass of stuff around these galaxies has not been slowed down. So it is kept up with the galaxies that have just gone straight through each other. So most of the mass in this system has not been slowed down. It's not interacted with other mass as it goes through. The actual gas, the normal stuff that we think about when we think about matter, has interacted. In other words, there's huge quantities of stuff here between and around the galaxies that's just passed straight through each other. So this is probably our best evidence that dark matter exists. There is something there. Other kind of competing theories for modified, we call modified Newtonian dynamics, so other theories of gravity don't account for this very well at all. What this is showing us is that the dark matter has gone straight through and kept going. The hot gas is slowed down. So this we call the bullet cluster. As I say, one of probably the best pieces of evidence for dark matter that we have. So now that's all well and good. The problem is, what actually is dark matter? Now there's a lot of different ideas and theories, ranging from the extremely small on this side to the extremely large on this side. So extremely large being like 10 times the mass of the sun, extremely small being some of the smallest particles that could possibly exist, and everything in between as well. You can see there's quite a variety of different ideas about what it might actually be. Out of all these, probably the two most prominent ones are this one, WIMPs, we call weakly interacting massive particles, so bigger than like protons, but don't really interact very much with light and the electromagnetic spectrum, so mostly interact through gravity. And one that we call, where we go, axions, which are a theoretical type of particle that we don't know that much about, but our standard model of particle physics predicts that an axion-like particle might exist, and it seems to have a lot of the same properties as a hypothetical dark matter particle. So it's like particles that are predicted by other theories, which gives them a certain level of credence, if you like. And it's kind of the same with WIMPs. They're also predicted by other theories, which is why they think they're quite strong candidates. A lot of these, and I see with all these other ones, I'm not going to go into detail about all of these because I want to talk about more than just dark matter in this talk. But just give you an idea of the range of different things. This one, primordial black holes, we will come back to later because this is of interest in a different area as well. Now, so that is dark matter. You may have also heard of dark energy. Now, dark energy we know a lot less about, but it seems to be much more of it even than dark matter out in the universe. So I guess we could start the story back with 1924 when Edwin Hubble proved the existence of other galaxies. A few years later, in 1929, Edwin Hubble proved that these galaxies are receding away from us. The universe is expanding. We're now fairly comfortable with this idea. So the universe is expanding. However, in 1998, a group of scientists proved that not only is the universe expanding, but it appears to be accelerating in its expansion. They later won the Nobel Prize for this in 2011. So what is causing this expansion? The answer is we don't really know. Beyond the fact that it seems to be accelerating in expansion, we have not had really any other indicator, particularly of what this actually is and what's causing it. And it seems to defy our understanding of fundamental forces as well. All the other fundamental forces attract. So magnetism attracts, gravity attracts. Whatever this dark energy stuff is, it seems to be repulsing, pushing stuff away. So none of our models, our understanding of physics and cosmology gives us anything that pushes away. So it's a huge mystery, and there's an awful lot of money at the moment going into tracking lots of deep space objects to get a really pinned down idea of how exactly they're accelerating away. So there are some scientists that think that maybe we're just misinterpreting this data, and if we interpret it in a different way, this accelerating expansion will disappear and not exist anymore. So there's an awful lot of debate between scientists about whether this is real. I mean, it's generally accepted that it probably is real, but again, this is how science works. There's always people who are doing their best to come up with a different idea. So in terms of dark matter and dark energy, as I said, there's an awful lot of money at the moment going into finding out more about this. There are literally dozens of experiments going on at the moment and planned to work out what's going on here. So from space-based telescopes, including 2 upcoming ones, one from NASA and one from the European Space Agency. We call the Roman Space Telescope and the Euclid Space Telescope. Particle accelerators, like at CERN and other facilities. Ground-based telescopes, underground detectors, where we can put something way underground to try and shield them from cosmic rays and other things to see if we can find the very, very rare chance of a dark matter particle interacting with a normal matter particle. Some theories suggest that they would interact very occasionally, and various different attempts at doing that. So far, nothing, though. We have not yet found anything. We've ruled out a lot of things, so we kind of know a lot more about what it's not than what it is at the moment. But nevertheless, hopefully, within the next few decades, we might know more. But probably this is one of the biggest areas, really, because it's so much. It's like, if normal matter, we think, if our kind of theories are correct so far about this, normal matter makes up about 24% of the universe. All the rest of it being, oh no, it's less than that actually. The vast majority of the universe being stuff that we don't know what it is or how it works. Now, with dark matter, it might be a combination of several different things. It might not just be one. It might be a whole hidden universe that we don't know about. And finally, on this note, I think I have an image for this one. Yeah, cool. We have something called fast radio bursts. The first one of these was detected in 2007. Since then, we found thousands of them as well, these fast radio bursts. So very, very, very high power radio signals, but lasting for milliseconds. Probably this is something spinning around, as we say, very, 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 very fast. This image, by the way, is quite a famous radio telescope. If any of you know your James Bond movies, this radio telescope featured in the movie GoldenEye from 1997. It is a radio telescope. Sadly, now it was destroyed by a hurricane a couple of years ago, so it no longer is with us. But this is one of kind of our iconic radio telescopes. Just last year, one of these fast radio bursts, the MIT in Massachusetts, kind of proved this is coming from a neutron star. Doesn't mean that all of them are, but at least some maybe of these fast radio bursts are from neutron stars spinning around really, 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 really fast. But again, we see lots of them from all over the sky. So I think hopefully within the next few years, we might know actually what these fast radio bursts are. 6, okay. So in terms of things that are coming up, we have a lot of radio telescopes that are being built at the moment. This one is in Australia. It is part of a technological demonstration for something we call the Square Kilometre Array. So this is the kind of the first version of it, where we have like multiples of these. We can see some in the background there, spread out over a wide area, and that acts a bit like one massive telescope. So when we had the previous image, we had one big dish. These days, what we tend to do is build lots of small ones, because it's like having an even bigger dish, just not quite in as good resolution. But with a bigger size of dish, we can see much smaller things in the sky. So this kind of telescope should be able to give us a lot more detail on things like these fast radio bursts. And in terms of X-ray telescopes, all our X-ray telescopes are getting a little old now. This is a proposed mission by the European Space Agency. We hope maybe in the next decade, we'll call it Athena, for the next generation of X-ray telescopes because, as I said, it's still relatively new. We need to put a telescope up in space to do it. We've only really been able to do that for a few decades now. So there's still an awful lot to be discovered in these higher energy. So again, hopefully within the next few decades, we should know an awful lot more about X-ray signals and gamma ray signals. So how are we doing? Yeah, so the next thing I'm going to talk about is black holes. I don't have as many pictures here of real things because we've not really imaged many black holes, right? We have a couple, which I'll pull up at the end, which you might have seen already. Something that started life as a bit of a theoretical construct, these. So when Einstein came up with this theory of general relativity, he came up with an equation, but actually coming up with a solution for it, like an answer out of this equation, is notoriously difficult. So the first person to actually come up with like a solution was not Einstein himself, it was actually somebody else. And the solution he came up with is what we now know as the black hole. So to make a solution for these equations, you basically simplify them down a lot. So the simple case for a black hole was to say if you have something that is incredibly heavy and dense in the middle, then what kind of happens on the outside? And what it suggested was if you had something small enough and dense enough, then you would have a region of space around it, what we call the event horizon, where nothing is actually able to escape. And for quite a long time, people thought this wasn't really a real thing, right? We have a lot of things that come up in mathematics that turn out not to be real, just a kind of interesting mathematical solution to Einstein's equations. But I think over the decades, it started to be taken more and more and more seriously, that this might be a real thing. And in the 1970s, somebody came up with this. Now, in the 1970s, computers, you had to use punch cards to program them, right? So this was created using punch cards and hand drawing the dots, the results that came out. What this is a representation of what a black hole might look like. Now, if you guys have seen the film Interstellar, I have a slightly more modern, updated version of this that you'll have probably seen, the giant black hole in Interstellar. But way back in 1977, no one had ever done this before. So this was what we thought a black hole would look like if it actually existed. So now inside the black hole, past this event horizon boundary, which is this black bit in the middle, where nothing can escape from afterwards, is where we really don't know what's going on. So what Einstein's theories suggest is that all the matter gets infinitely dense, gravity gets infinitely strong, and time and space start to get extremely strange, let's say. A lot of people think that maybe this is just a problem with the maths, and if we kind of manage to get quantum mechanics and general relativity to actually work together, which they don't at the moment, then this will sort of sort itself out. And some people suggested that we would never actually be able to see inside these things and see the bit in the middle. The thing is, with this original solution to the black hole that I mentioned before, that came up with their idea of the event horizon, this was for an object that's not spinning. But as we know, pretty much everything in the universe does spin. So when we actually run simulations of spinning black holes in certain circumstances, suggests that this event horizon might not appear. Actually, some scientists think it might be possible that we could actually see the singularity being the infinitely dense point in the middle. So it might be possible that we can actually see what's going on in these incredibly dense environments. So there's scientists out there looking to see if they can see signals of these what we call naked singularities, which if we could get information about these things, would go a huge way to giving us a theory of everything, right? At the moment we have the theory of the very small, quantum mechanics, and the theory of the very large, general relativity, and they don't work together. The maths just they don't play nice. So we might find out more if we can see naked singularities, if indeed that's a thing that exists in the universe. Something else that I mentioned before was primordial black holes. So, this is an image, by the way, of what we mean by the singularity. So a black hole bends the very fabric of space around it. so extremely that this is kind of outside the black hole. This is kind of a 2D representation, like a whirlpool. So if you are an object or a spacecraft or something, you get too close to the black hole, you'll be pulled in and down. So the fabric of space-time is being stretched and distorted so much that it becomes infinite at the bottom. This is a sort of 2D representation of what the gravitational field around a black hole might look like. It's a bit difficult to visualize in 3D. This is why we kind of do it this way. But yeah, so there's the way that black holes exist now in the modern universe is when enormous stars die. They tend to explode in what we call supernova, and the core collapses down into a black hole. We call these stellar mass black holes because they come from stars that are about the same mass as a few times the mass of the sun. And we also see, as I said, these enormous supermassive black holes in the center of galaxies. And we maybe have intermediate mass ones as well. But smaller than a stellar mass black hole, there's no way, we'd think, in the current universe that these can be created. However, in the early universe, just after the Big Bang, in the first sort of 400,000 years, there was so much stuff so packed together and so hot that some scientists think that maybe black holes were able to just spontaneously form from the closely, densely packed material. If that was the case, then a great many of them would still exist today. They would just be incredibly small. Or they could be of any size arbitrarily, but there would be a lot of incredibly small ones. We call these primordial black holes. The problem really is finding them, because they're so small that they don't really distort enough space-time around to see them unless you just happen to be looking in exactly the right place, exactly the right time. So it's still up for debate whether these primordial black holes actually exist. As I said, if they were created, there's every chance they could still be there. Some scientists have even suggested these could go into the core of a star and you would never know the difference. And some people think also it could be the source or one of the sources of dark matter. If there's huge quantities of these primordial black holes just still floating around, this could be the dark matter that we're looking for. Maybe. And, oh yeah, so I'm not going to go into a maths lecture here, don't worry guys, but this is an equation come up with by Stephen Hawking, probably one of the other really famous scientists of the 20th century. Stephen Hawking tried to find a way to marry together general relativity and quantum mechanics at the boundary of a black hole. What he came up with was this idea that black holes actually radiate small quantities of thermal radiation. They are not just things that absorb everything, eat everything, but actually maybe they emit small quantities of heat. They call this Hawking radiation. Now this equation, what we're looking at, this one is the Hawking temperature. Most of these things are constant, so these basically stay the same. This is the mass of the black hole. What this basically means is that the temperature of the black hole is inversely proportional to the mass. In other words, when the mass of the black hole is bigger, the amount of Hawking radiation is less. When the black hole is smaller, the amount of Hawking radiation is more. So much so that if you made a black hole of a very small size, if this is true, then it would explode instantly, right? But if you have an enormous black hole, it would give us such small quantities of Hawking radiation, be incredibly hard to detect. So because the only black holes we can see are pretty big, right? It's quite hard. We struggle even to see the big ones, let alone small ones. We cannot detect any thermal radiation, any small quantity of thermal radiation coming off them. So we don't actually know if this is true or not. It would have quite a big consequence if it was true. If a black hole emitted small amounts of thermal radiation, give it sort of a long enough time period, then the black hole would actually shrink and eventually evaporate. Or if this is not true, then it wouldn't, and it would be eternal and live forever. So it has quite a big consequence of what actually might happen towards the end of the universe as to whether this is a real phenomenon or not. Nevertheless, most scientists think that it probably is at the moment. That's the kind of going consensus on this, although we're not by any means totally sure. And what we've got here is quite a famous little animation taken over 16 years, if I remember correctly. This is of the center of our galaxy. So we are looking at stars going around, an empty patch. There's nothing going on here, but they seem to be doing something very, very strange. So you can see the stars going around, and they seem to be all orbiting this point. So we looked at this spot for a number of years, and we got these orbits going around, and then using this, we can work out actually the mass of the thing in the center. What we worked out is somewhere within this period of this patch of nothing, there's about 3 or maybe 4 million times the mass of the sun. So a lot of stuff in there that we couldn't see. This was our indirect evidence of the supermassive black hole in the center of our own galaxy. These days we've done a bit better, actually. Recently we've used something we call the Event Horizon Telescope to image the black hole. So we've actually imaged 2. The first one is on the left here in this giant galaxy called M87, and the other one here is R1. So this is our 4 million times the mass of the sun, which would fit into a space a bit smaller than the orbit of Mercury. And then this one, this monster in M87, is significantly larger. We can see the orbit of Pluto here would be fully inside it. And the furthest away space probe that we have sent, the Voyager space probe, which is about now 1 light day away from us, would still not really have cleared the event horizon, right? So this thing is an absolute monster. What we did to do this is use 8 telescopes spread across the world. So if we can have a bunch of telescopes spread apart to make one big one, if we spread a bunch of telescopes over the world, we can essentially make a telescope the size of the Earth, just with not very great resolution. That's why it's really fuzzy. And we use this to image, as I said, first M87 and then our own black hole. But we don't really have a good idea of how such a large thing could exist. How these black holes actually form and grow. When you run the calculations, as if it was a bunch of small ones coming together over the life of the universe is not old enough for these size of black holes to actually have existed yet. There's some other process that formed these, and they seem to form pretty early in the history of the universe as well. When we use the James Webb Space Telescope to look back into the distant past, we see black holes which have formed and grown at a rate that we can't really explain at the moment. So one of the big areas of science at the moment is to try and explain how these massive black holes actually formed and how they grew. It seems to be a relationship between the size of a galaxy and the size of the black hole in the center. Pretty strong relationship, actually. It seems to be, there must be some kind of link between them. It seems fairly obvious. Coming up in the future, we have a few sort of new experiments. This, by the way, actually is an image of the magnetic field lines around the black hole in the center of our galaxy. So we can use the polarization of light to get this rather beautiful image, which looks a bit sort of clearer as well than the previous one. And we do simulations as well to give us an idea of what it might look like, what to actually look for. So this simulation is of 2 supermassive black holes, which are about 40 orbits away from colliding. So we want to try and find black holes that are merging together. So using both telescopes that look using light and X-rays and things like that, but also using telescopes that measure the very fabric of space and time. So these objects are so large that when they collide together, it causes ripples in the fabric of the universe. This was predicted by Einstein, and just about a decade ago, we detected the first ones. Gravitational waves, we call them. So we can look for both these gravitational waves, and we see black holes merging using these gravitational waves. We see the signature from them. But we have not yet detected any black holes of this size merging, partly because the detectors we have are not the right size to do so. Right, so upcoming in the future, we are building gravitational wave detectors that are bigger and will allow us to maybe see these things actually happening. Because again, when we do simulations of galaxies coming together, so the main way this would happen, two big galaxies merge together. Eventually, the black holes will be pulled towards the center of mass of the system. They'll be slowed down by moving through the rest of the merging galaxies, and eventually they'll get sort of 3 or 4 light years away from each other. After that point, we're not sure how, what mechanism causes them to slow down more enough that they can actually merge. So we think it would happen. So we don't know the mechanism to where they actually get this close to each other. We think it probably will happen, but we don't know how at the moment. Let's go. So upcoming, we have our kind of next generation of Event Horizon Telescope. So the one that allowed us to image our own black hole. So NGEHT. So we're adding hopefully a number of other telescopes to get much better resolution on these things, including one proposed one here, where we are, in Canterbury. And there's a number of others that were not included on here as well. And the goal of this as well is to get not just an image of the black hole, but actually to try and get a little bit of video and see how it is evolving over time. And this is our kind of most ambitious gravitational wave detector. So we're making it bigger by putting it out into space. So 3 different satellites that are separated by hundreds of thousands of kilometers, shooting lasers at each other to measure tiny ripples in how this fabric of space-time changes. So that will be launched fairly soon. We call this one LISA. So we've already had proof of technology launched for LISA, and hopefully before too long we can actually get it running and we can start to see these larger merges of really big objects merging together. So how are we doing? Oh yeah, just about on time. So the final thing I'm going to talk about is the early universe, progenitors. So in the early universe, we think that things were quite different. We think the stars were quite different. We think that the makeup of the universe and galaxies was quite different. So one thing that people are very, very interested in is the early stars. So actually, quite quickly after the Big Bang, we think the particles formed within like a few minutes. We get the first particles forming, but actually nearly 400,000 years until the first atoms actually form. So we get protons and electrons forming, but for quite a long time they're way too hot to actually combine together. So eventually the universe expands and cools down enough that we get atoms forming, and then after a couple of 100 million years, we should get the first stars forming. But what do these actually look like? There's kind of 2 leading theories about what the first stars might have looked like. They would have probably formed in the similar way to stars form at the moment. So when stars form, we start off with big clouds of hydrogen gas and other dust and things like that collapse down under gravity. And this tends to form multiple stars now. So we may get hundreds or even thousands of stars forming from the same cloud of gas. We think in the early universe, because it was a lot hotter, actually a whole cloud of gas would collapse down and form just a single star, something that is called a population 3 star. So it would be much, much, much bigger than our current stars. So if this is our sun, our kind of population 3 star is going to be enormous. And also wouldn't last very long. So actually there's only a small window in the universe where these things could actually exist. And the James Webb Space Telescope is currently looking for these to see if we can find any population 3 stars, these massive early stars, before the universe got too big that they wouldn't form anymore. The other leading candidate is something called a dark star. So this is one of the images from the James Webb Space Telescope doing a sky survey. So taking a big area of the sky to have a look for different objects. And some researchers have picked out these 3 kind of little blobs that might, they say, be something called a dark star. So this is an incredibly large object, bigger even than the population 3 star, which is a mixture kind of between helium, hydrogen, and lots of dark matter. The dark matter, we call it dark matter annihilation, is keeping the thing hot. So it's not a star in the way that we normally think of it, and they could be much, much, much bigger, maybe like 1,000,000 times the mass of the sun. And these researchers suggest that maybe the supermassive black holes that we see now were formed from these dark stars dying eventually and collapsing. So they're about the right kind of size for that. Although, as said, I wouldn't call it proved by any stretch of the imagination, but they say these three objects might be that, potentially. And we also look with James Webb Space Telescope at galaxies forming. So the kind of conventional wisdom at the moment on this is that galaxies merge together from smaller groupings and build up over time. So we get smaller groups of stars forming, merging together, merging together, merging together until we get the galaxies that we see today, all kind of mediated by large quantities of dark matter holding everything together. When the James Webb Space Telescope started operating, we saw these, what they call little red dots. These strange objects that sort of defied explanation a little bit. There's a couple of, again, leading ideas about what these things actually might be. Some researchers suggest they might be early supermassive black holes, being very, very hot and energetic and pulling in lots of material. The main problem with that is that we don't see any X-rays associated with these. Supermassive black holes these days always have large quantities of X-rays. There's lots of energetic matter around them. These are not producing any X-rays. The other idea is that maybe they are very, very densely squeezed galaxies. So huge quantities of stars in a really small area. But we don't really have a good model for how that could be in the first place. What it might be is galaxies that are not rotating very much. So with our Milky Way, because it is rotating quite a lot, we get this big disk shape of spread out stars. Maybe if there were galaxies that formed without huge rotation, they could end up in a really dense ball of stars. These are the two kind of leading theories for what these objects might be. Hopefully, we will find out soon. That one. So, if we want to see some of the oldest objects in the universe, we could look into the deep, distant past, or we could just look nearby us, around the Milky Way. We see extremely old objects around the Milky Way. This object is something called a globular cluster, which some of you are probably familiar with. We find 159 of these around the Milky Way. We see them around other galaxies as well. And they're very, very useful for lots of things, for lots and lots of science, but we don't have a good understanding of how they formed in the first place. Some of these seem to have formed before our Milky Way galaxy. Some of them might have been the cores of small galaxies that were absorbed into the Milky Way when it was forming. And we also find small galaxies, dwarf galaxies, orbiting around the Milky Way, which seem to have formed in the first billion years after the Big Bang. So we can also look nearby us to find old things. But it's not clear what the relationship is between galaxies forming, globular clusters, dwarf galaxies, and larger galaxies like our Milky Way. Although these are very common and, as I said, very useful for a lot of things, still not well understood. Perhaps in the next little while we might know more about it. And so, what we've also done in recent years is map the locations of galaxies around us. This is what we call our local supercluster of galaxies. So there's about 100,000 galaxies in here. So the kind of nearest, you might say 100,000 galaxies. This is kind of what it looks like. We're up here. It's a local group. That's kind of us. Local group being us and the nearby galaxies to us, not just our own galaxy. Well, we know that the universe is expanding away from us. But if we look at the motion of these galaxies and we subtract that universal expansion, take that away, then we see there's a small residual motion of these galaxies associated with the overall gravitational pull of the cluster. And when we kind of map that, we get something that looks a little bit like this. So again, we can see our little galaxies here. And these lines are these small residual motions when we take away the universal expansion. What we see is that they are kind of going together. So there's There's a motion towards the center of gravity of these galaxies, and we see that all this supercluster is all moving towards a point here. We call this the Great Attractor. The main problem about this is the location of that is directly behind the Milky Way from our point of view. So the body of the Milky Way is exactly in the wrong place for us to see what is there, why there is such a huge concentration of stuff there that's pulling everything else in the local universe towards it. So the Great Attractor will probably remain a mystery for at least 50 million years or something until we've orbited around the Milky Way far enough to see it. For now, all we know is that that seems to be the main concentration of mass in the local universe. So how are we doing? Nearly out of time, or a little bit over. So finally, a couple of the upcoming things to answer some of these questions. First of all, we have the fully finished square kilometre array, which we are working on at the moment. So this will be in 2 locations, in Australia and in South Africa. It will, when it's completed, be the largest radio telescope in the world, which will allow us to see with unprecedented levels of detail. We obviously have the James Webb Space Telescope here, which, although it is working at the moment, it still has a lot of things to tell us. There'll still be a lot of new science that will come out of it. Up here, we have the Lunar Crater Radio Telescope. The idea of this is to put a telescope on the other side of the moon. So the side of the moon that is facing away from the Earth, so that it is shielded from interference from the Earth. The idea is this will be a 1 kilometre wide radio telescope. So not as wide as something like the square kilometre array, but with much less interference, and it will be a better resolution for its size. It's a pretty advanced idea. I hope it will get made. And then the current plan for the successor to the James Webb Space Telescope that we call the Habitable Worlds Observatory. This is the proposal for this one down here. So a bigger telescope than the James Webb. The main aim of this one is to try and find life around planets, exoplanets, planets around other stars. So I hope that I've given you a good overview of where we are with science at the moment, what we have upcoming to answer some of these big questions, maybe an impression of how little it is we actually do know about the universe. So I hope very much that you've enjoyed it. Thank you very much for coming, everybody. Yeah, enjoy the rest of your night.